When you listen to a piece of music or feel the temperature shift throughout the day, your brain registers a continuous flow of information. But a computer cannot process that unbroken physical reality. It does not hear notes, chords, or the rising trends of a stock market. Instead, it receives a strict sequential list of numbers. It takes snapshots of a changing quantity, freezing isolated moments in time. Engineers call this numerical sequence a digital signal. Look at this split. On the left is the flowing real-world data. On the right, the computer's reality, a raw vertical table of discrete measurements: 25,350, 25,352, 25,349, 25,355. The entire discipline of digital signal processing rests on the mathematical translation between that smooth analog curve and this rigid column of data. To see how this works, we will build the exact mathematical notation required to slice a continuous wave into a finite sequence, and then apply the discrete Fourier transform to extract the hidden cycles within those numbers. To understand this process, you have to let go of your intuition of time as a flowing river and adopt the machine's perspective, reality as a static indexed array. This graph plots a continuous physical event, like room temperature. We write this as x of t. The lowercase x represents the physical signal itself, and the t tells us it changes continuously. But when a processor begins sampling, the continuous line disappears. We are left with fixed data points, and the notation shifts to x of n. This new equation, x of n, defines the sampled digital signal. The sequence is built from individual snapshots. X sub 0 is the first recorded value, x sub 1 is the second, x sub 2 is the third, and so on. Notice that the number inside the bracket is completely separate from the recorded measurement. That inner variable, n, is the sample index. It serves one specific function. It tells the computer the exact position of the data point within the sequence. If you call for x of 100, the system does not look for a value of 100. It retrieves the 101st recorded measurement from the array. We define the absolute boundary of this dataset using a capital N, which represents the total number of recorded samples. By swapping t for n, time is successfully frozen. A flowing physical event becomes a static, computable list of numbers. Here is the standard mathematical model for a continuous wave. The amplitude a and the frequency f operate inside that flowing time variable t. A processor cannot calculate infinite fractions of a second, so it takes measurements at strict intervals. To solve this, engineers replace the flowing t with a discrete formula, n times t sub s. This requires establishing a sampling frequency, denoted as f sub s. This tells us exactly how many times per second the computer will record a measurement. From that, we derive t sub s, the sampling period. This is the exact physical gap of time between each measurement. If you set the sampling frequency to 4 Hz, recording 4 times a second, your sampling period is simply 1 divided by 4, or 0.25 seconds. This chart shows how the index n clicks into place against that physical time gap. The first sample hits at 0, the second at 0.25 seconds, the third at 0.50, and so on. Each one of those perfectly timed snapshots locks in as a single indexed value in our new discrete array. Time has not been erased from the data. It has been mathematically embedded into the exact rigid spacing between the numbers. This time domain array, x of n, securely stores raw data. However, it is functionally useless for revealing the overlapping cyclical patterns driving that data. Joseph Fourier recognized that any complex sequence of data can be broken down and viewed as a combination of independent, overlapping cycles. To extract those cycles from our array, we use the discrete Fourier transform. This equation is a bridge. It translates our original time domain signal, lowercase x of n, into a frequency spectrum, represented by the capital X of k. The k represents the frequency bin, acting as the index for our frequency domain output. The mechanism inside the formula relies on core mathematical components. Sigma sums all the samples, while Euler's number e, the imaginary unit I, and pi calculate rotation. In practical engineering, this operation takes the raw signal and measures exactly how much of it aligns with a specific rotating frequency. Do not confuse this specific discrete algorithm with the continuous Fourier series or the heat equation. Those deal with infinite variables, while our equation operates on a strictly finite set of numbers. The discrete Fourier transform proves sequential data and frequency data are mathematically equivalent. They represent the exact same reality, analyzed through a different numerical dimension. When applying this in modern software, you will use the Fast Fourier Transform, or FFT. This is not a new mathematical formula. It is simply a highly efficient algorithm designed to compute the exact discrete equation we just built. This chart shows the FFT output. When you run a chaotic dataset, like our nifty stock sequence, through the algorithm, the resulting X of K chart isolates the distinct cycles driving the noise. But in fields like computer music, engineers utilize a powerful property of this math. The process can be run entirely in reverse. Rather than recording a sound and analyzing its cycles, you can start directly in the frequency domain to build a signal from scratch. The process often begins by generating a discrete impulse train, a mathematical time buzz that naturally contains equal amounts of every possible frequency. By operating directly on this flat spectrum, engineers can mathematically increase or suppress the energy of specific harmonics, sculpting entirely new audio profiles. This shaped frequency data is then passed back through the inverse transform, synthesizing into a playable digital sound wave. Digital signal processing circumvents the fundamental blindness of computers. By translating continuous physical reality into static arrays of numbers, we can perfectly analyze, rebuild, and manipulate the analog world using strictly discrete mathematics.